Welcome to this deep dive. Today we're going to crack open a really crucial concept, hypothesis testing.
Yeah.
Think of it like, I don't know, your personal detector for claims based on data. Is this pattern real or is it just, chance?
Exactly. We've got some good stuff here that gets into how it all works.
Right. So our mission really is just to unpack it for you, make it make sense.
And the core idea, it's actually pretty straightforward when you break it down. You start with a kind of default idea, the nothing interesting is going on scenario.
It's the null hypothesis.
That's the one, the null. Then you look at your data and ask, okay, is this data weird enough, different enough to make us doubt that nothing's happening idea? And if it is, maybe we lean towards the alternative hypothesis that something is actually going on.
Okay, so it's like trying to find evidence against the status quo. Now, you often hear about one-tailed or two-tailed tests in studies. What's that about?
Ah, yeah. That really just depends on your question. Are you looking for any kind of difference or a difference in a specific direction?
Okay, explain.
So say you're testing, I don't know, a new teaching method. If you only care if it improves scores, specifically better, that's a one-tailed test. You're looking in one direction.
Got it. Higher scores only.
But if you're just interested if it changes scores at all, maybe better, maybe worse, you'd use a two-tailed test. You're open to change in either direction.
Oh, okay, that makes sense. Direction matters. Now let's talk about that number you always see, 0.05, the alpha level or significance level.
Right, alpha. Think of it as your risk tolerance for making a specific kind of mistake.
Which mistake is that?
It's the risk of rejecting the null hypothesis, saying something's happening when actually nothing is. It's a false alarm, a type I error.
So 0.05 means there's a 5% chance we'll raise that false alarm, even if the null is true.
Precisely. And yeah, 0.05 is super common, but it's worth remembering it's, well, kind of arbitrary. It's a convention, not a universal truth.
Good point. So we're trying to avoid crying wolf. But what about the opposite? What if there is a real effect and we just miss it?
That's the other side of the coin. That's a type 2 error. Failing to reject the null hypothesis when it's actually false. You miss a real finding.
Ah, okay. So there's a trade-off.
Absolutely. There's this tension between avoiding false alarms, type 1, and not missing real effects, type 2, and things like your sample size play a huge role here.
How so?
Well, generally, a larger sample size gives your test more power.
Power meaning?
Power is the probability of correctly rejecting the null hypothesis when it is false. So, bigger samples usually make it easier to detect a real effect if one exists, reducing your risk of a type 2 error.
Okay, that tracks. Now, we often see things like z-tests and t-tests mentioned. What are these actually doing?
They're essentially tools, test statistics, that summarize the evidence from your sample. They calculate a number that tells you how far your sample result is from what you'd expect if the null hypothesis were true.
So like a signal-to-noise ratio, kinda.
In a way, yeah. Different tests for different situations, like t-tests are really common when you're comparing the means, the averages of two groups.
And I remember reading that these tests, like the t-test, they have assumptions. Things need to be right for the test to work properly.
Oh, definitely. For a standard t-test, you're assuming things like your observations are independent, the data within each group is roughly normally distributed bell-shaped, and the variability, the spread of the data, is similar in both groups.
And if those assumptions aren't met,
then the results of the t-test might not be reliable. You might need different methods.
okay, so that covers averages. But what about comparing percentages? Like, say, the proportion of people who click on ad A versus ad B?
Yep, there are different statistical tests specifically designed for comparing proportions between groups too. Hypothesis testing is quite flexible.
So once you have your test statistic, how do you actually make the call? Reject the null or not? I think there's something called a critical value.
Exactly. The critical value is like a threshold. It's determined by your chosen alpha level, like 0.05. You calculate your test statistic from your data, and if it falls beyond that critical value,
Then you reject the null.
then you reject the null. It means your result is statistically significant, unlikely to have happened just by random chance if the null were true.
And how does this relate to confidence intervals? I feel like they often come up together.
They're very closely related. Think of them as two ways of looking at the same evidence. A confidence interval gives you a plausible range for the true value you're trying to estimate.
Right.
Now, if that range doesn't include the value specified by your null hypothesis, like, say, zero difference between groups, then your hypothesis test would usually be significant at the corresponding alpha level.
Ah, I see. So if the 95% confidence interval for the difference doesn't include 0, the p-value for the test of no difference would likely be less than 0.05.
You got it. They offer complementary information about the uncertainty and the evidence.
Okay, so wrapping this up then. Hypothesis testing is essentially a structured framework. It helps us use data to decide if an effect we're seeing is likely real or just chance, while always acknowledging we might be making an error.
That's a great summary. It's about making informed decisions in the face of uncertainty.
So here's something to chew on for you listening. Now that you've got this framework in mind, how might it change the way you look at stats or claims you see out there, maybe in the news or in your own field? It's a really powerful lens.